Public key cryptography gives digital identity a new foundation, proving you control an account without revealing your secret. A private key can create public proof through addresses and signatures, powering blockchain wallets, passwordless login, and secure messages. So far, we've built two foundations: how blockchains record transactions through ledgers and consensus, and how web apps recognize users through logins, sessions, tokens, roles, and permissions. Public key cryptography connects those worlds. It explains digital ownership today and prepares us for wallets and passwordless authentication next. Digital identity creates a paradox. You need to prove you control an account without handing over the secret that protects it. Cryptography solves that problem with mathematical proof, turning trust into something others can verify. Symmetric cryptography is like two people using the same secret key. It is fast and practical for bulk data, but the challenge is sharing that secret safely. Public key cryptography changes the model. One key can be shared openly, while the private key stays protected. That makes it useful when strangers need to communicate, verify identity, or prove that a message came from a specific owner. A key pair begins with the private key. Think of it as the master secret. It creates digital signatures and proves control, so it must never be shared. From that secret, software derives a public key. The public key is safe to distribute because the math works one way. Others can use it to verify signatures, but they cannot work backward to discover the private key. Whoever holds the private key controls access. Behind the scenes, that private key starts with secure randomness. The system creates an extremely large random number, and that number becomes the private key. A cryptographic algorithm then derives the public key from it. This direction is critical. The public key can be shared, but it should be practically impossible to reverse the process. If the randomness is weak or predictable, the whole account is at risk, which is why real wallets rely on trusted cryptographic libraries. A blockchain address usually starts with a public key, then gets transformed through hashing or encoding into a shorter, cleaner identifier. That address is what people paste into wallets, payment forms, and block explorers to send crypto or check activity. But the address is not the source of control. Control still comes from the private key, because only the private key can create valid signatures for actions tied to that address. Think of a digital signature as proof of approval, not as a hidden copy of the private key. The signer combines the exact message or transaction with their private key to produce a signature. Later, anyone can use the public key, the message, and the signature to verify it. If verification succeeds, the message has not changed, and it was signed by the private key holder. The private key stays secret the entire time. For a blockchain transaction, the details alone are not enough. Your wallet signs the exact sender, recipient, amount, and fee with your private key. Nodes then verify that signature using public account information. If it matches, the transaction can move forward and be included in a block. If anything was forged or changed, verification fails and the network rejects it. The same signing pattern can support login. Instead of asking for a password, the app creates a fresh challenge, often called a nonce. The wallet signs that exact message with the user's private key, without exposing the key itself. The server checks the signature against the user's public key or address. If it matches, the user has proven key ownership, and the app can grant access. In this model, a key pair can function like a digital identity. The public key or address is the label others can recognize. The private key is the secret that proves control, like the only key that opens a door. When you create a valid signature, the system can verify it and grant access. But that trust depends entirely on the secret. If someone steals the private key, they can impersonate you. Usernames and passwords rely on a shared secret. The user must remember it, and the server must store something derived from it, usually a hash. If that database leaks, attackers get a target. Key-based identity changes the proof. The server asks for a signature, while the private key stays with the user. That reduces server-side risk, but it raises the stakes for backup, device loss, and recovery. A digital signature turns a message into a verifiable statement of intent. If the signature checks out, The system knows the private key holder approved that exact message. Change even one detail and verification fails. That is why signatures are so powerful in blockchains. They prevent others from spending funds they do not control. The same principle supports secure login, where signing a challenge proves ownership without revealing the private key. Public key systems give users strong control, but that control depends on protecting private keys. Never share keys, seed phrases, or recovery secrets. Back them up safely. Use trusted wallets and devices, and verify what you sign. If a key is lost or stolen, access and authority can disappear instantly. You now have the foundation. Keys create ownership, addresses identify accounts, and signatures prove control. Next, we'll see how wallets make this usable.